In this presentation, gang, we're going to talk about numerical integration. And you've already seen an example of numerical integration when you wanted to calculate the area under a curve using a Riemann sum. So as a reminder, I have an example right here. The blue curve is the basic square root function, okay? And I'm going to approximate the area under it with a series of 6 rectangles, okay? And they're going to have all equal widths. And that's just for the sake of simplicity, right? We know from our work in Calculus 1 that a Riemann sum doesn't have to have rectangles that all have the same width. Eventually, you're going to take the limit as the number of rectangles increases without bound. So it all comes out in the wash. So, but to ensure that the widths of the rectangles will all be the same, we always use this little formula right here, delta x equals b minus a over n. Okay, that's where n is the number of rectangles. You'll notice also that I'm using a left-hand Riemann sum. And so what that means is for every one of the subintervals, I use the left endpoint to establish the height of the rectangle. I highlighted those heights with those red dots that you see there, and then I labeled all of those dots, okay? Now, in order to calculate that area, we know we just do length times width, add up the 6 integrals, the 6 rectangles, and approximate the area. We don't have to approximate the area because we know we can find the antiderivative of the square root of x. What I want to point out to you, though, gang, is this. Notice how much of the area under the curve is unaccounted for. For example, here. Okay, and then there's some right here. And then here, and so on. Okay, so that would amount to the error in your estimate, right? It doesn't account for all of that area. So, but that's okay, we were just going for an approximation. If you want to reduce that error, that shaded green stuff that I just put there, then use more rectangles, okay? Now consider this. Suppose instead of rectangles, and this is the idea behind numerical integration. Suppose instead of rectangles, gang, we did this. Watch this. We used a trapezoid instead. Okay, look at what it did, gang. It reduced the error in the approximation, right? If you think about it, if you use trapezoids, you can actually reduce the error in using rectangles. Let's draw another one. Let me use a different color this time. Okay, isn't that clever? So actually, when you think about it, using trapezoids to approximate the area is going to reduce the error, and is it a better approximation than using just rectangles? So the method that we're going to use is called the trapezoid rule. All right, let's do this. Let's draw all trapezoids. And I won't shade them in this time, kind of makes it cluttered. All right, there's the first one. Here's the second one. And so on. Okay. All right, now let me remind you that the area of a trapezoid okay, there's our trapezoid right there. And you can find this in the front cover of any textbook, gang. The area of a trapezoid is 1/2 times its height. Now this one is standing on end, Okay, so the height right here, ordinarily we would say like this. Okay, so 1/2 the height times the sum of the lengths of the parallel sides. Okay, so 1/2 times the height times the sum of the lengths of the parallel sides. So in our case, right, all those purple trapezoids right there, all of their heights are identical. They're all equal to delta x equals 1. Let's write down all of those areas. Okay, so for the first one, 1/2 times its height, which is 1, times the sum of the lengths of the parallel sides. Now that's where we need the y coordinates, right? That the y coordinates of all the points you see listed there. The y coordinates give you those heights. So the first one, right, the first parallel side, that height is square root of 1, plus the next height, square root of 2. Okay, and then carry on until you get them all. Okay, so for the second trapezoid, 1/2 times 1 times the square root of 2 plus the square root of 3, and so on. Okay, and then I'll simplify all that. I'm going to remove the common factors, the 1/2 and the 1. Okay, and then I'm going to add up all of the roots, right? We're taking out all the common factors here. So now I'm going to add up collect like terms. So I'm going to have square root of 1. Notice I've got a square root of 2 here and here. So that means I'm going to have 2 of those. In a similar way, I'm going to have 2 square root of 3s, and so on. Okay, and then we would just at this point, gang, this is just a calculator problem. You could throw all of that into your calculator. Okay, excuse me, and if you do, you'll find that that's approximately equal to 11.65. Okay, now the true value could be found just using this. Okay, so you wouldn't use the trapezoid rule on something that you can find the antiderivative of readily. Okay, it's a great approximation method when you can't find an antiderivative. Okay, so I want to point out a couple of things though. Notice, gang, that there's a pattern here. First of all, we have our 1/2. And then the 1, remember that was delta x. That was the height or the width. And in the parentheses, notice that there's a series of 2's. Okay, that's a pattern that always occurs, gang, when you use this trapezoid rule. Okay, that's what this is called, the trapezoid method or the trapezoid rule. Okay, so let's generalize. let's say we have some function y equals f of x. Okay, from A to B. We want to break that up into n trapezoids whose heights are given by this formula. All right, let's call that, and we'll say x of 0, just to be consistent with notation, is x of 0, and b is x of n. We would draw our trapezoids. Okay, and then find that the area is approximated by 1/2 delta x times the sum. Okay, notice getting the pattern of twos. The pattern of twos does not extend to the first and the last term, so just be aware of that. And once again, the whole thing is typically a calculator problem. You know, spreadsheets work especially well for these kind of numerical techniques. Okay, so I want to approximate this integral using n is equal to 5 trapezoids. So I'll make a note here. The heights of all those trapezoids can be found using this formula. So 3 minus 2 divided by the number. Okay, so 1/5. So again, what I'm going to do is I'm going to exaggerate the picture so we can see it better. Okay. So what you want to do is you want to start from 2 and go over to 3, and you want to count in increments of 1/5. Okay. Right. Be mindful that the number 2 is 10/5. Okay. So you can draw the curve if you like. Okay, and that's up to you. We're going to approximate the integral, so we actually don't need it. What we need are those hash marks. That's really what it comes to. Okay, so I'm not even going to bother drawing the curve. Oops. Okay, I'm going to make a note that the function in question is 1 divided by the logarithm of x. Okay, so keep that in mind. Okay, so symbolically, that's what the whole thing is going to look like. The next thing you would do, as I said, as I mentioned before, is you would just simply input all of this information into your calculator. Or if you like, you can even use, as we mentioned a moment ago, like a spreadsheet. What you have to watch out for this, gang, is, in fact, I did it myself. If you notice on that last term, I almost put it, well, I did put it 2, but I had to erase it, right? I actually had to erase that. So just be mindful that the first and the last terms, right, do not have 2's in front of them. However, everything in between will. Also, the delta x, right, that figures in right here. It's common for students to forget that. So do be aware of it. The next thing we'll do is we'll input this into a calculator, and I'm going to do that right now. that took a little while to type all that in. Sorry, gang. But here's what I get. Okay, and that assumes approximating to 3 decimal places. If you want more accuracy, then use more trapezoids. Okay. All right, now I'm going to make a note here. In a similar way, and I'm going to say using polynomials, we get the next numerical method, and it's called Simpson's rule. Okay, it's similar to the trapezoid rule, right, where you can approximate the area under a graph. Actually, you can just approximate an integral, okay, a definite integral. This is called Simpson's rule. The amount of algebra that's involved in it, gang, I think I'm going to forego that, and I'll just state the rule directly. All right, so here's how it goes. Okay, so instead of a 1/2 delta x, it's 1/3 delta x. Okay, 1/3 delta x. On the inside of the parentheses, okay, now in Simpson's rule, notice that like the trapezoid rule, where there was a pattern within the parentheses, all twos in between the ends, in the Simpson's rule, there's a pattern as well, and that pattern is 4, 2, 4, 2, and it continues that pattern where it oscillates, for lack of a better word, between the 4 and the 2, okay, until the last term, the term before that, rather, which ends in a 4. Now, to guarantee this pattern, where the second term starts with a 4 and the next to last term ends with a 4, we stipulate n must be an even number of subintervals. Okay, n must be an even number of subintervals. Okay, so here's an example of using Simpson's rule. All right, so I'm going to use the same function I did before, okay? But instead of 5, I'm going to use n is equal to 6. All right, so here is what we were working on before, right? Approximate the integral from 2 to 3, 1 over the logarithm of x dx, but instead of using 5, we're going to use n is equal to 6. Okay, now the hash marks, let's get those. And once again, I'm going to exaggerate like we did before, just so we can see better. All right, so we're going to start at the 2, and we're going to count all the way over to the 3 in increments of 1 over 6. Okay, I'm going to make a note to myself that 2 is the same as 12 over 6. Okay, how does that look? Okay, and you can see plainly the 6 subintervals. Okay, you can see them all. But then once again, because it's a numerical technique, what we really need is this formula right here, and just simply the hash marks along the x-axis. So we just plug all of them in. Yeah, I just noticed something. I've got a 16 where I should have a 17. Okay. And once again, gang, simply put, this is all something that you would plug into your scientific calculator, or you could just set up a very easy Excel spreadsheet to calculate these things, okay? Now, I keep the number of subintervals kind of small because this is a rather tedious process. But if you set up an Excel spreadsheet, right, that you can use as many subintervals as you like. You know, you can use, for example, in the trapezoid rule, you could use 30 or even 50 trapezoids if you like. The Excel spreadsheet will calculate, right, make the calculation with the snap of a finger. Okay. Simpson's rule and trapezoid rule are two very good ways to approximate an integral when the fundamental theorem doesn't work for you. And what I mean by that is if you cannot find a suitable antiderivative to make the exact calculation.